Good morning, everyone. My name is Kristen Vanderwall, and I'm the Product and Marketing Manager for Hendrix Overhead Solutions. I'll be your host for today's webinar titled High Voltage Conductors, the 69 kV and 115 kV Spacer Cable Solution. This webinar completes our four-part fall series, and we sincerely appreciate everyone's participation. Our 69 kV and 115 kV spacer cable solutions offer a myriad of benefits. In this presentation, our Director of Technology and International will detail the key features of each, as well as the critical issues they address, making them an ideal solution for utilities wanting reduced right-of-way, increased ROI, and environmental protection. As for today's format, we will begin with a 60-minute PowerPoint presentation, and we'll follow that with another 30 minutes of Q&A for a total of 90 minutes. Many of you are already familiar with the Q&A tab located at the bottom of your screen. During the presentation, please use this tab to submit your questions. I'll be screening the questions as they come in, and we'll relay some of them to our presenter during the presentation. Then, as time allows, we'll address all other questions during the Q&A segment. Anyone who submits a question that we do not have a chance to get to will receive a response in writing from us. Now, I'd like to introduce you to today's presenter, Mr. Brian Traeger. Brian is a senior member of the IEEE. He received his Bachelor and Master's of Engineering degrees in Electric Power Engineering from Rensselaer Polytechnic Institute in New York in 1979 and 1980 respectively, and a master's degree in business administration from the University of Pittsburgh in 1986. Brian has held various positions in engineering, consulting, and management at American Electric Power Company, Cooper Power Systems and Fisher Pierce, as well as Hendrix Wire and Cable, where he's been for the past 26 years. He has taught electric power engineering at Ohio State University, West Virginia University, and Pennsylvania State University, in addition to teaching courses to utility clients. He has authored over 50 technical papers and articles for the IEEE and other national and international organizations. He has brought to fruition numerous high reliability power distribution projects in various sites on all 7 continents over a period spanning more than 40 years. Now, I'd like to turn things over to you, Brian.
Thank you for that wonderful introduction, Kristen. Hello, webinar participants. Thank you for taking the time out of your busy schedules to join us today. It's for me personally, it's a privilege and a pleasure to be able to share our ideas and technology with you. So without further ado, we'll get right into it. Topic, as Kristen told you, is high voltage covered conductors, what we're calling the 69 kV and 115 kV spacer cable solution. For our outline, again, we'll have to start with an intro. We'll get a little bit into the history. We'll talk about what the high voltage covered conductor system objectives are. Then we'll get right into 69 kV. We'll talk about applications, components, testing, construction, and as well as the history. And then we'll get into 115 kV, what we're calling the next generation. Talk quickly about components, construction, and we'll tell you a little bit about the pilot project we've had going here for a couple of years and give a status update on that. Just one quick slide on history, introduction. Again, we've been around since 1951. This is not a new technology. We've got 70 years in covered conductor technology. We started out at 5 and 15 kV, quickly went to 25, 35, 46 kV. We went to 69 kV in 95. So we've got, 25, 26, 27 years in that. And 2 years ago, almost 3 years ago, we went into our 115 kV pilot. We're on all 7 continents. We've got over 75 countries installed. We've got continuous development, continuous improvement, and we're installed for reliability, economics, safety. And as I always say, spacer cable is not, it may not be for everywhere. It's a design option, and we've got to keep that in mind. So spacer cable is basically, it's a compact system. We've got covered phase conductors. You can see the high strength messenger on top, and we'll describe that a little bit. The spacers are made of high density polyethylene so that they're the same material as the conductor covering, so we don't find ourselves with any dielectric incompatibility issues. The system is mechanically strong and it can withstand tree or animal contact without damage or without reliability issues. Sorry about that. So what are our objectives here? First of all, we want to minimize right-of-way requirements. That's very important in a transmission line. We want to have the ability to add circuits in an existing right-of-way, whether that's a new pole line or perhaps putting multiple circuits on an existing pole line. We might want to have a voltage upgrade in the same right-of-way, take a 25 kV right-of-way, replace the poles, put in 5-10 feet taller poles, and put a 69 kV on that same pole line. And have the ability to add circuit without increasing pole height. And we'll take a look at this a little bit later. We're going to have reactive voltage support and improved voltage regulation. We know that we've got, say, 15% less impedance, so we're going to have 15% voltage regulation. And improved reliability. We're going to have the ability to withstand momentary contact with trees and animals without having a fault. Certainly going to reduce tree trimming or increase the cycle length. We're going to reduce EMF, we're going to have, which is not a big deal here in the US these days, but it's we're going to get 80% reduction in EMF compared to bare wire lines and up to 95% reduction compared to underground lines. We're going to promote environmental stewardship, and we'll discuss this in a brief moment. And close phase spacing can reduce pole height. And lastly, you know, the other justification or motivation for high voltage covered conductors is where basically underground or bare overhead is either too costly or you just can't do it. The implementation problems exist. So you're looking for a solution where you have very few options. Okay, so this is just, I've got a couple of slides thrown in here, just show you some of the benefits. This is a system we have down at Pepco in Maryland where a tree fell on the line, the 69 kV line. They have helicopter patrols every 6 months. This was found by a helicopter patrol. There was no outage. They went out and they removed the tree and you know, the line survived. So if this had been bare wire, everything would have been on the ground. That 69 kV line, as well as the 1525 kV underbuild below it. This is another system we have. And this is in the bottom of South America, in the bottom of Chile. Basically, we did a ring loop, 69 kV ring loop around the city of Pucón, and where it went through the national park, there's Villarrica National Park. We used spacer cable, so that looked quite nice there. And we spent a lot of time with the EPA in the country of Chile working on this project. So I always use the word environmental stewardship. And you know, what does that mean to us as power engineers in the utility business? Well, we basically want to have tree trimming reduced by 80%, where we want to coexist with the trees. We don't want to remove all those trees. We want to preserve wildlife. We want to preserve migratory bird species. We're going to have EMF fields vastly reduced. And we're also going to have the benefit of storm hardening, resiliency in the face of major weather events, which we seem to be having quite a few. And we have all these great photos. People, and you know, engineers send us these photos, so I can't help but share a few of them where we've got, you know, tree-dwelling animals, whether they're you know, anteaters or three-toed sloth or what have you, or the migratory bird species, or just, you know, bald eagles and so forth, that coexist quite nicely with the covered conductor systems that are APLIC compliant. There's another great photo. There's the same park in Chile, runs through the area. This is a great photo. Also talk about environmental stewardship, you know, doing UNESCO World Heritage Sites around the world, which we didn't really notice that 20 years ago, but as I started keeping track, we've done quite a few UNESCO World Heritage Sites. And here's in the Galapagos Islands in Ecuador, in the Pacific. And here we're protecting one of the migratory bird species that was perishing, flying into bare wire lines. So we're very proud of that. Here's a system we have on the South Island of New Zealand. You can see where it runs into the national park. It immediately switches over to spacer cable. And this is a 34.5 kV transmission line, but the point is well made that we're using spacer cable at UNESCO World Heritage Sites for environmental stewardship. And of course, I have to show you a photo. We said we're on all 7 continents, so I had to show you a photo of the spacer cable in Antarctica. And this has been there since the 70s, and we send down spare parts every couple of years, but this is done, performed admirably. So where are we installing these 69 kV systems? It's all over the place, but we also have, I wanted to I'll show you some urban settings. So here's a system we have in Nebraska, in the city of Omaha, and this is running through the city. So that's, more or less an urban setting. We have a bunch others. Here is one we have in Ecuador, in Guayaquil, and this is to power a mass transportation system. And we can see it here. So this is an overhead tram that is bringing commuters to the city in from the suburbs, and the suburbs are across the river. So that's a very high reliability system there. So we're very proud of that. We'll take a look briefly at the components. For the cable, we're using the same exact cable that we're using for 15, 25, 35, 46 kV. It's a 3-layer cable. It's compact, double AC. We know we're getting more ampacity. We don't need rated tensile strength because those phase conductors are not under any mechanical tension. So the double AC will give us lower weight, higher ampacity, and the ability to compact it so that we'll use less polyethylene. Polyethylene is expensive, so we want to reduce that cost. And with the lower diameter, we're going to have a lower profile to wind and ice and what have you. So that will have benefits both for weight, for the poles, and for the guys. We're using a semi-con shield to minimize partial discharge when we are in contact with a ground plane. The middle layer there is high molecular weight polyethylene. That's a natural unfilled polyethylene. It's translucent. You can see right through it. That's going to give us a very high BIL. And it's also going to provide strip ability, meaning that when I put that spiral stripping knife into the outer layer, it's going to go into the inner layer and strip quite easily. So that's quite functional as well from an operational standpoint. The outer layer is where we put a lot of the tricks. That's high density polyethylene, and we're sourcing the highest high density polyethylene that we can source in order to give us a very high abrasion resistance, because there is some anticipation that this will be in contact with a tree at some point. We don't want that jacket to abrade and cause us issues there. It's where we put our UV inhibitor, and that UV inhibitor is a chemical UV inhibitor. It is not fugitive. It's not carbon black. It's a chemical UV inhibitor, and it puts an umbrella on the molecular chains, protecting them from UV radiation. It's where we put our track resistant data, and it's also where we put our color. So that's what we got there for the cable. And if you compare that to a 15, 25, or 35 kV system, you would see the same 3-layer system of insulation, only difference in thickness. The messenger, we're going to use AlumaWeld or AlumaWeld aluminum, which is basically, it has a heart of galvanized steel with a 10% cladding or coating of pure aluminum. If we need more ampacity, we're going to take out some of those AlumaWeld strands and replace them with pure aluminum strands. And that's what we call AWA, AlumaWeld aluminum. That's going to have several functions. It's going to be the mechanical strength member. It's going to hold everything up in the air. It's also going to act as a system neutral. It's going to act as a lightning shield for that transmission line. And it's also going to keep things that fall on that system from above from damaging those phase conductors. And we'll see a few photos on that as well. Here is our spacer. Again, it's from the same injection molded gray high density polyethylene. It's going to have the same dielectric constant to avoid dielectric incompatibility. We're going to get a suspension clamp that's going to clamp that spacer directly onto the messenger, so there will be no walking. We're going to have a long leakage distance, and it's going to have the same self-washing shed design that we have on our lower voltage or medium voltage spacers. And you can see the DM clamp there. That's going to give you more, that's going to have a positive connection to the messenger, so it's not able to walk horizontally. A couple of years ago, we decided to do some design improvements on that spacer. We wanted to prevent twisting of the spacer cable close to spoles, especially at the corners. We wanted to add a new degree of freedom, a new degree of rotation by allowing the whole spacer to rotate at that messenger connection point. So what we did is we added two firm, rigid arms in the center, what we call a horizontal beam. So we replaced those two beams with one beam, which is a reinforced fiberglass. And that fiberglass can handle a much higher stress and is more rigid than the previous two arms. We ran the mechanical finite element analysis and tensile tests to verify that new design from a mechanical standpoint. The electrical specification of both designs are identical. Electrical tests will be done on the new spacer when that comes in, which is hopefully it's already in. And here's the areas of improvement. You can see on the top, we replaced the messenger clamp with one that will give it an additional degree of freedom. And we replaced the two center horizontal beams with a single overmolded horizontal beam that's going to give it a lot more rigidity, if you will. And here is the additional degree of freedom you can see up in the messenger position. So that'll work out quite nicely for us. Here's some of the FEA plots. You can see what we did in FEA. We put 400 pounds of downward weight on each of the conductor positions. And you can see the stress there in the rod. So the max stress in the fiberglass rod with the 400 pounds in each position is about 2,800 PSI, whereas the tensile stress of the rod is 28,000 PSI. So with that simulation, which we thought was safe for a 954 with snow and ice, we've essentially got a mechanical safety factor of 10. So that'll serve us well as we move out to larger conductor sizes. Let's talk briefly about the laboratory tests we did on this system when it was in design in the early 90s. And again, this was developed with some consultants that we hired, basically National Electric Safety Code consultants, and we worked with Florida Power and Light with their Juno Beach labs in Florida. And these consultants also basically suggested which tests we should do. So the first one was AC breakdown, the second one was impulse, and the third one was a U-bend discharge. So the AC breakdown, and we had a couple of samples here. We did a 636 and a 795. We knew what the AC breakdown was going to be because we know the AC breakdown of high density polyethylene, exactly what it is. But anyway, we had to do the test. So we got an average of 218 kV for 5 samples, which is about 5.5 per unit for line and neutral voltage. So that's pretty darn satisfactory for AC breakdown. We took the other sample, the 795, we got the same data, 214 kV, again, about 5.5 per unit for the line and neutral voltage. So that is also very satisfying. We then took samples in and we did with the Marks generator, the impulse generator, if you will. We had 4 samples that we tested, could not break them down. So they all completed the 962 kV step, which was the limit of that impulse generator. So the bad news is I can't tell you the BIL of that cable. The good news is that I can tell you that it's in excess of 962 kV. Again, so that is the BIL of that 69 kV cable. The BIL of the system is going to be much higher because you're going to have to add in the BIL of the spacer in the air or whatever distance you are to the ground plane, in which case here is the messenger. Then we did a U-bend discharge test. This is not, this was recommended by our consultants. We said it was not relevant. This U-bend discharge test is for underground cable, underground 69 kV cable. We did it anyway. Basically, you bend it, cable in a U, you put it down on a steel plate, you energize it at 100 kV, and you go the time limit. And if it doesn't fail, you've passed the test. So the test results confirm that there's no danger of immediate failure when a grounded object comes into contact with that cable. As far as poles and structures, we've essentially, at 26, 27 years in, we've installed 69 kV on basically every type of structure there is out there on the planet: wood, steel, modular poles. We're using the height as required to obtain the required clearance. You can see the davit arm there. Our standard davit is 1.25 meters. And we also will do engineering review. Either we'll select the pole for you, or we'll do an engineering pole verification for the poles that you select. This diagram comes out of an IEEE paper that was published in the 90s and showed a project was partially justified by the fact that by switching from bare wire to spacer cable, this utility was able to take 21 feet off of their pole height. So this was quite an accomplishment. Show you a couple of diagrams here. Here's a tangent pole, pretty simple, using the same davit arm with a kind of like an MC4 clamp to sit the messenger in there. We no longer put the spacers at the pole, we put them on either side of the pole. So that's a slight difference, but not much of a difference. Here's another photo of Pepco. They have a lot of 69 kV spacer cable on the Pepco system, and they run it down residential streets, which looks quite nice. Here's a light angle pole, or light angle poles rather. We're basically installing them more or less like tangents up to 15 degrees. This is a vertical double dead end. And this is in vertical rather than horizontal. This is a river crossing. It happens to be an inaccessible river crossing. This is a river for lava when there is lava. So that's nice. Here's a 90-degree angle pole. We're basically dead ending the cables on both sides, running them right through the preformed dead end grips without cutting or opening the cable. Here's what it looks like during installation. And this is what it looks like after installation. So it's very clean. Here's a transition to bare wire. And again, this is a vertical transition. So we're coming through the preformed dead end grips, standing off that pole with a line post insulator, and just making a crimped transition on the other side to the bare wire. And you can see the lightning arrestor there that is necessary when we have a transition from bare wire to covered conductor, the same as you would use an arrestor on a riser pole. So that was a vertical transition. Here's a horizontal transition. And again, we've worked with utilities. Anything they want to do, as long as it meets National Electric Safety Code, we're happy to do it. This is There's a triple circuit in a city called Natchitoches. Forgive me for mispronouncing that, in Louisiana. They had a 132 kV bare wire on top, a 15 kV bare wire on the bottom, and they wanted to install a 69 kV bare wire. I believe what happened here is line crews balked. They said, there's no way we're working on bare wire in between 132 and 15 kV. Switched that to spacer cable and saved a tremendous amount of vertical clearance there. And oddly enough, as soon as we installed that, it was hit by Hurricane Katrina. In 2005, bent up a couple of spacers, but it survived. And then it was hit again last year with Hurricane Laura. So we're very happy with this system, and it's performed admirably in the face of severe weather. Get back to the system that we have in Chile. This is quite scenic because there's a famous volcano. There's a famous area for vacationing. So what we did here, we had 69 kV on top, and we put a 25 kV spacer cable underbuilt below that. So nice. This is a double loop transmission loop that we have in the state of Massachusetts, in the center of the state there. So there's a very active bird migratory and conservation area. So that loop is being replaced with spacer cable. And as you see here, on the left, this is a double ring loop. So we replaced the one on the left with spacer cable. I assume at some point they'll replace the one on the right with spacer cable. This had an incident probably 7, 8, 9 years ago where there were a couple of trees fell and put the whole ring out. Massive outages in a tri-state area. So something had to be done, and this was the solution. There's also a technical paper written on this by one of the engineers from National Grid that is available should anybody ask for a copy. And we've got all kinds of systems out in beautiful, wonderful places like the Caribbean here. Here's St. Lucia Electricity, Lucelec, and we're running right through the national park. If anybody's familiar with the pitons, this is where you go to visit to view the pitons, if you will. And we have a spacer cable, 69 kV system there. So that's 69 kV spacer cable. How about 69 kV tree wire? We have a client in Canada that did not want to use spacer cable. They wanted to use tree wire. They weren't sure if spacer cable was yet approved by CSA. Today it is approved by CSA. This was several years ago. So they went with a tree wire configuration, fully tensioned. And they did a brilliant job. Here is, it's on line post insulators with suspension clamps covering the covered conductor. And we can talk a little bit more about this on an offline, if you will, but that's a tension pole. Here's a light angle pole, again, using the line post insulators for standoffs. Here's a heavy angle pole using suspension insulators with the same IPC connectors. And here's a close-up of the heavy angle pole and the 69 kV dead end. So that's a 40-kilometer line through a national park in Alberta, Jasper National Park. Performed admirably, and that also has a 25 kV underbuild on a good portion of that line, although not here, as you can see. So to sum it up with the 69 kV, we've got various design utility environments. We're in North and South America, the Caribbean. We're allowing multiple design options and configurations, whether it's vertical or horizontal transitions. We're using every kind of pole we've got on the planet, and we're able to design it to satisfy local standards. Our engineering support includes development of the complete material list, including non-Hendrix items. We do the sag and tension calculations and the clearance calculations. We can either select for you or assist with the selections of poles and davit arms. We have complete detailed pole construction drawings, complete instruction for installation, and we have field supervision and training during installation. Our installation specialist will be with you on site, pre-construction and construction, to make sure everything goes perfectly. And these services and field support are all included in our standard one price project package at no additional cost. So there's no worrying about where all of this is coming from a cost standpoint. We've been in successful operation for 25, 26, 27 years. It's mechanically and electrically reliable. It's proven to be a viable 69 kV transmission system. Okay, so that's 69 kV. 115 kV is going to go very similar, but I'm going to shorten it a bit. I'll talk about 115 kV, our objectives, design approach, the spacers, what they look like, the other components, the installation method, and then some of the drawings, if you will. So again, what are our motivations? This is going to be the same thing that we talked about with 69 kV. We want to improve reliability, reduce vegetation removal, vegetation management. We want to reduce right-of-way requirements. We want to allow additional circuits to be built in that right-of-way. We want to make it easier and faster to get regulatory approvals for new right-of-way or perhaps right-of-way expansions. We want to preserve the environment while expanding those transmission capabilities. We want to minimize public relations issues due to line location, routing, design, EMF, and we want to help utilities meet their goals for reliability and environmental stewardship as stated in their strategic direction, mission, vision, and regulatory agency targets, their regulatory roadmaps, if you will. Design approach is the same. You know, as I said, 69 kV is the same as 15, 25, 35, 46 kV, the same as with 115 kV. The conductor design is exactly the same. It's the same 3 layers of insulation, semicon strand, the natural high density Miller layer, and the HDPE outer layer. Let's take a look quickly at the spacer here. The spacer is really different when we go to 115 kV. So this is not drawing the scale, and I apologize for that. But the 25, 35, 46 kV space, I didn't show the 15 kV spacer here, but the 25, 35, and 46 kV spacer, you can see that's 24 inches high. When we go to the 69 kV spacer, now it's a full 63 inches. When we go into the 115 kV spacer, yeah, you know, it's 3.5, 4 times the size of that 46 kV spacer. So it's starting to get a little bit large. We also had some mechanical issues. So, you know, when you get a spacer that large, you really can't mold a piece of polyethylene that big. I guess you can mold parts, but they would not be strong enough. So what we did is a spacer top support bracket that's made of 853 grade B pipe with the Vangs ASTM A57265 structural steel. The spacer arms are basically fiberglass rod over molded. So it's basically suspension insulators, if you will. They're designed by us and made by us. The covered conductor there in the clamp, we have the cable clamp. We have thermoplastic cable inserts. It's going to increase the insulation around the cable at the point of connection to that spacer. And then we have the messenger attachment. Let's take a look a little closer. The cable clamp and insert assembly was basically have a high density polyethylene sleeve that's going around the conductor before it gets into the clamp. And that sleeve is going to smooth out the voltage gradient, give us more insulation at that connection point. The spacer assembly itself is these parts. And you can see you have an extra degree of freedom at the messenger connection and at the cable connection, okay? And here's what it looks like in our test yard. Is the spacer itself, the suspension insulator, if you will, that is the spacer arm, the clamp, and the cable inside of that. Installation. Well, we say, we're going to have a hybrid installation method. We're basically going to use the pole by pole method. We use 3 shiv blocks at 50-foot intervals. Again, so instead of having the spacers every 30 feet with 15, 25, 35, 46, and 69 kV, when we go to 115 kV, we're going to have spacers every 50 feet. So that is one obvious difference as we go to 115 kV. We're going to have continuous poles up to 2,500 feet, depending on the conductor size. If it's a smaller conductor, would do more than that. We're going to have extension bar position conductors close to the cable clamps, as you can see here. 3 phases are going to be pulled together with minimal tension. At angle structures, we're going to hang single shiv blocks from each line post insulator. And we're going to install the spacer close to the block and transfer the conductors to the cable clamps. And as with other voltages, we're going to sag those phase conductors according to a table. And again, the conductors will be slack. There will be no mechanical tension in those phase conductors whatsoever. So I thought I'd show you some of the construction drawings with some photos. Here's another difference. So at the tangent, we didn't want to put the spacer at the pole. The spacer's getting a little bit large. We're trying to keep compact construction. So we're using line post standoff insulators at the poles to go for a tangent structure. This is going to be a 7 to 25 degree angle. Again, we don't want that conductor getting close to the pole. So we're going through the dead end grip on one side. We're pushing it away from the pole with a line post insulator, and then going back into the preformed dead end grip on the other side of the pole. There's going to be a heavier angle, 26 to 60, basically very similar construction. And here's a 90-degree pole. I guess the difference here is that we don't need a standoff insulator. There's enough standoff from the pole that we don't need to ensure that that phase conductor is pushed away from the pole, because we don't fear that it will ever touch the pole. So that's what that looks like. And here's one way of doing it anyway. There's a 115 kV dead end transition to bare wire. So again, you can see here we're coming out of the dead end grip around a standoff insulator, and then making that connection directly onto the bare wire. And of course, we have our lightning arrestor there to prevent any lightning surges hitting that bare wire and getting into our covered conductor. I want to give a status update. So, we started this project around 2008, and I guess we started it with a very forward-thinking utility, Bonneville Power Administration out west, and they saw the need for taking care of their right-of-ways, making sure they have reliability, making sure that they're not cutting too many trees. And they were interested in the 115 kV. So we submitted a proposal to the Department of Energy, and we did not get the money. And I'm thankful for that. So we ended up developing it on ourselves without Department of Energy money. But basically, it took us to about 2019 till we had this figured out. Our design team in Milford at Hendrix figured this out. So by 2019, they had all the lab tests done. They had the insulators figured out. They had the assemblies figured out. They had done the BIL test, the AC withstand test. We did all sorts of testing on partial discharge, all sorts of testing on mechanicals. And by November 2019, we had our pilot installation, and we were happy to be hosted by a company called Emera, which is now called Versant Utilities in Maine. So very happy to have that. Our design consultant that did design for that system was TRC Consultants, and the installation contractor was good old USA Construction. That's done a lot of work with us, both research and a lot of the construction around for the local utilities. So in that 2 years from November 2019 to today, we've gone back every 3 months and done PD, partial discharge monitoring. We're using a company called Exactor, which I believe is the leading company in the US for PD monitoring. They do quite a nice job. They do multiple data point input assessment analytics, do predictive analysis, and they really do a great job. So that assessment and review is ongoing. We went there again every 3 months. Last year, we went and we took down a whole bunch of components and replaced them, brought those components to the laboratory. We analyzed them for tracking, cracking, any type of electrical erosion. And we found that the system was working quite well. So again, it's, we've got 2 years with this, and it's just plugging away at 115 kV without any problems. Our first commercial line is in design today, and that will be installed early 2022 in just a couple of months in the state of New Hampshire. So we're very proud of that, and that will be not far from headquarters. So people who visit us will be have a very simple time going out and visiting that line. So I may have spoken a little bit quickly, but forgive me. The participants of today's webinar may request a certificate of completion to submit to your PE boards for CEU credits, or by contacting your local Hendrix representative, or emailing Kristen, which is kvanderwall@marmonutility.com. There will be a brief survey when this webinar concludes, and we'd greatly appreciate your participation. And with that, I will hand it back to our moderator, Kristen Vanderwall, and see if there are any questions. And thank you so much for your attendance today, your participation, and I hope to see you on a future high voltage covered conductor project. Thank you very much.
Thank you very much, Brian, for that excellent presentation. We did have a couple of questions, which we'll go through now. The first one, if you have a 2-mile line to build and it's mostly clear right of way, but you do have some areas with dense trees, is it possible to just install several spans of spacer cable, or can you go back and forth between bare wire and spacer cable?
Yes, Kristen, great question. Yeah, we do this all the time. We build lines through national forests, whether it's 25 or 35, 46 or 69 kV. And, you've got 2, 3, 4, 5 mile line. You don't want to pay the premium for high voltage covered conductor. Yes, we'll do 2, 3, 4, 5 spans here of spacer cable. Then we'll do maybe, a half a mile of bare wire, then a quarter mile of spacer cable, and half mile of bare wire. Yes, you can go back and forth between bare wire and spacer cable. I guess the only caveat is that you got to buy a couple of arresters, because every time you do a transition between bare wire and covered conductor, you have to install arresters to prevent that covered conductor.
Thank you very much. Yes, next one. Is this system intended for major transmission lines? For 69 and 115 kV, what's the limit in terms of conductor size or MVA?
Yes. Okay. So for 69 and 115 kV, I guess the largest conductor we could make today would be a 954 kc mil. And that is the limit of our extrusion facilities at the moment. That hopefully will change in the future. So I think a 954, if you went through the calculations, that would be good for about pretty close to 100 MVA. If you did that same at 115 kV, I'd have to do a calculation that would probably be more, more like 150 MVA. So yes, it is for major transmission lines. But again, we do have those limitations of up to 954 kc mil.
Thank you. And how well does this system fare with forest fires?
Good question. That's another topic. So forest fires. You know, we've done presentations on wildfire mitigation. That's a long topic, but let me see if I can just dance around this topic. Okay, so if you have a static, I've been called out personally on forest fires with covered conductor down at Smoky Mountain National Park in Tennessee. We had a forest fire past spacer cable because they run it up the ridges to their I guess their fire and their antenna farms. So we had the utility call and say, hey, we had a forest fire, come on and take a look at the cable. The forest fire must have been moving. It was good for a couple of days. Rain put out that forest fire. The poles were singed, they were burned, they were blackened. We went up in a bucket and we analyzed the cable, and it was okay. There was no issues. We had another one, the famous fire of Gatlinburg. I forget the year, where they burned down a couple of city blocks. It was, and the spacer cable was right next to it. Again, the poles were singed. The cable was not damaged. Now, that's not to say that if I had a static forest fire, okay, so the forest is on fire. There's very little wind, it's not moving, and there's a lot of fuel. You know, if I've got 1900 degrees Fahrenheit at a height of 25 feet in the air, yeah, that's that high density polyethylene is going to melt and it's going to come down, but probably everything else is down already. So how do we fare in forest fires? Pretty darn good, as long as it's moving. If it's static, nothing's going to survive.
Thank you. Next question is, does Hendrix have any plans to pursue higher voltages like 138 kV or 145 kV in the future?
Yeah, it's not on the drawing board. Do we have plans, hopes, and visions? Absolutely, positively, beyond the shadow of a doubt. To me, you know, for being in this industry 43 years and being at Hendrix for 28 years, the only way we can do is go up. I mean, environmental stewardship is more important every year. Tree preservation is more important every year. You know, trees eat carbon dioxide, for crying out loud. We shouldn't be cutting them as much as we are. So yeah, can we bring this to 138? Absolutely. Can we bring this to 145 kV? Absolutely. Can we bring it to 230 kV? Absolutely. But that will take some time. That will take some investment on the part of Hendrix, and it will take some participation on the part of our industry. But do I see that? Beyond the shadow of a doubt.
Thank you. And you mentioned that there's an increase in spacer spacing to 50. It seems like with more weight, you may want to stay at 30 or maybe even reduce. So what's the reason for the increased spacing?
The reason for the increased spacing is that number one, we would like to go up to 60 or 50 or 60 or 70 feet if we could, but we don't want to have conductor clashing. So there was a limit where we could say, okay, we're going to have some blowout on those individual phase conductors, and they're still not going to connect with each other if we go out to 50 feet, but maybe 60 feet would be too much. So we're trying to minimize the spacers. We're trying to minimize the weight we're hanging on that messenger, because now we just don't have those phase conductors and some very trivially 15, 25, 35, 46, 69 kV spacers that weigh almost nothing. Now we've got a real meat and potatoes steel spacer out there that weighs a lot, with three very large suspension insulators on that spacer. So it's getting heavy. So it's kind of trying to work in harmony electrically and mechanically with not getting too much weight on that messenger. I'd like to push it out past 50. 50 feet is where we are right now. I hope that answered the question.
Thank you. If not, they can feel free to edit or add to that. Next question is,
let me add, Kristen, that anything I say here today can be backed up with a diagram, with a test report, with a client testimonial, with an IEEE paper, with an internal report. Any questions you have, you can send me and we will respond to those in a written professional fashion. Sorry.
Absolutely. No, thank you for that clarification, Brian. Next question, can you use OPGW in lieu of a messenger wire?
Yes, we can use OPGW, and when it's in the messenger, we call it OPMW. Yes, we do it. Yes, we have done it on hundreds of miles, maybe thousands of miles of 15, 25, and mostly 35 kV systems where we're having them at wind farms and solar ranches. So yes, that fiber can be put in the messenger.
Thank you. Would the 115 kV system work on a Canadian 120 kV class system?
Yeah, absolutely, positively. I would absolutely, beyond the shadow of a doubt. I'd have to do some calculations on yes, voltage, stress, and charging current, but off the top of my head, I would say absolutely, positively.
Thank you. And your presentation didn't touch on cost. So what's the typical cost differential between bare and spacer when you're talking about a 69 kV or 115 kV system?
Okay, and I apologize for not covering costs. Again, when we looked at this some years ago, first of all, when utilities are installing 69 kV spacer cable, it's not because they love us, it's because they really don't have a whole lot of options, okay? So they're doing it because it's an engineering, it's an operational decision. However, if we had to get down in the dirt and say, what's the cost differential? I would say that when you're at 69 kV, the multiplier from bare to spacer cable might be 2.5 as much as 3.5. I would say when we get to 115 kV, it's probably in that same range, but I don't have those numbers with me, nor am I aware of those numbers. But when we do this first commercial project, which is not a trivial project, when we do this first commercial project, we will have a better handle on those numbers. And when we do this in a year from now, I'll be able to speak more intelligently on that.
Thank you. Next one, is galloping an issue? And if so, do you recommend the use of dampers?
Okay, so when we talk about spacer cable, I know that there's a video out there of showing spacer cable galloping. I cannot explain it. I mean, if we've got, this happened decades ago, we've got over 500,000 miles of spacer cable. We've never had a galloping related failure. When we use spacer cable, we essentially have a vibration damper every 30 feet, right up to 69 kV. With 115 kV, we're going to have a vibration damper every 50 feet. It's going to be the spacer. So any standing waves that try to set themselves up on these spans will be damped by the vibration dampers, which are the spacers. Now, with that being said, when we get into a tree wire configuration, galloping is possible, the same as it's possible with bare wire. So, and we'll see this a lot in Europe when they have extremely high tension conductors. We can also see it here in the US and places like Indiana, where you have highly tension phase conductors and you have an ice storm. And just when you get a certain amount of ice, the natural frequency of that system is the same frequency of the wind, of its excitation, and it gets into a galloping situation. So it's possible on tree wire. highly improbable, statistically impossible on spacer cable for galloping.
Thank you. And it looks like this might be our last question. And when you are dead ending, what kind of cable are you using between the insulator and the pole?
Oh yeah, just a good old off-the-shelf line post insulator.
They asked what kind of cable are you using between the pole and the insulator?
Yeah, I don't understand the question. It's the cable, it's the or 69 or 115 kV cable. There is no other cable used. And assuming I'm not understanding that question, somebody can write that into me and I will give you we can chat offline or correspond offline via email.
Yes, absolutely. And that does conclude today's webinar in terms of questions, but if anyone has a question that pops up later, please feel free to reach out and we will respond in writing as Brian mentioned. Thank you again for your time today. As a reminder, a brief survey will appear in your browser once you leave the webinar, and we'd appreciate your participation. And we hope you have a great rest of your day and that we see you on future webinars. Take care.
Thank you.